Good afternoon, ladies and gentlemen. Welcome to Tech Gig Webinars, our endeavor to empower techies. We believe that sharing of knowledge is the key of enhancing our performances and for our growth as professionals. With this principle in mind, TechGig has initiated a series of webinars conducted by industry experts to give a crisp insight of various domains. Topic for today's session is Network Operating Systems for Evolving Networks. We are delighted to have Mr. Vanyarajan, DGM at HCL Technologies with us today. Mr. Vanyarajan has been working with HCL for last 16 years and a part of Cisco Odyssey since 1997. He has been designed in algorithm design for packet classification, OS infra development, software engineering, and architecting technical networks. Gentlemen, this presentation will continue for next 45 minutes and we will take your questions after the presentation. In the meanwhile, you can post your queries through the chat pane available in the webinar software. Without further ado, I introduce you to our guest speaker, Mr. Vanyarajan.
Hi, good afternoon everyone. It is my pleasure to reach out to all of you on this day, and the topic we are going to discuss for the next 1 hour or so is going to be on the network operating systems for evolving networks. Actually, I should say that this is going to be more of an introduction session because this is a very vast area where there are so many developments happening and there are lots of research that are going on in designing such operating system, for evolving networks. So I'll be presenting this this topic in 2 stages. So the first one would focus more on the motivation for the operating system itself and what's the principle behind it, and then I'll take few questions, and then we will move on to what are the fundamental design factors or considerations for network operating systems. So feel free to post your questions, and I'll try to answer them as much as I can. I expect this to be more of a very informative session to all of you. I hope you'll enjoy this. So just moving on. So what to expect from this presentation? Okay, so I've designed this presentation in a slightly different way, where you'll see a lot of white spaces and more of diagrams and pictures. So we'll be focusing more on the concepts behind these operating systems, the founding principles or the basic principles or the basics of these operating systems, and get a new perspective of the whole system itself. Instead of going with a conventional way of getting into a particular architecture view or getting into some implementation specifics, so I would be drawing your attention to look at the entire problem in a new perspective. And what not to expect. So I'm not going to cover any specific implementation of any specific operating systems, and we are not going to talk about an architecture of such operating system. And also I'm not going to pick up any case study here. And based on some of the feedback and based on some of the questions that could be raised in this discussion, maybe we can have one follow-up session in the same forum. I'll be happy to address that. And moving forward, so I actually, for most of this entire presentation will be of this style, where you don't see any pictures or drawings or any bells and whistles. So it's going to be some mere text, but it would actually provoke your thoughts so that you are able to understand things more from the fundamental perspective. So before getting into all the details, let's just define what's computing. So what do we mean by computing? So in general, the human brain actually involves in computing several things. It can be image processing, or it can be simple math, or it can be word crunching or language processing. So there are several things the brain does that. Okay, so inside the brain, okay, we have some finite states. Maybe you pick up an example like how do you do a math, right? So either you do a multiplication or division. So you basically at each step, you call it as a state where you're moving from one step to the next step. And use the finite symbols. If you look at it, the numbers or symbols or the alphabets or symbols, even the operators like let's say plus, multiplication or division symbol or mod arithmetic. So you call them as symbols. And then you would like to have infinite notebook. It's more like your mathematical notebook. You would like to have various notebook. You can just imagine that you have a math notebook with the squares, right? So each square you can write some symbols, and that actually helps you to do some computation. That's what you eventually do with computing. Now let's see what it means in the modern computer. So each square, analogically speaking, so they represent a memory location. And the finite states, the states are the intermediate steps, right? So you basically follow some sequence of steps before you arrive at the particular solution. So I call them as control sequence. And then you have finite symbols. So if you look at it, the operators, whatever that we write in the notebook, they actually tell you something. Let's say if it is 12 plus 12, you only do an addition. The same thing, if I change the symbol without changing the data, let's say if it is a multiplication, you will end up doing 12 into 12, which is going to be 144, right? So, but if you look at it, both the instructions on what you do with the data as well as the instructions themselves, they reside in the same notebook. Of course, that's the same case with the computers as well, where you have both the data and instructions reside in the same memory. Right? So moving on, so that's the birth of general purpose computing, where you started writing the code. Okay, so code is the actual word to represent the software, because it's basically coded. The instructions or the data are coded either in binary or hexadecimal, or basically you assign some sort of semantics, in other words, some meaning to these codes. Okay, these codes, when they are organized in certain ways, would accomplish a particular task or would solve a particular problem, right? So if you change the system will behave in different ways. So that's why if you look at our computers, they are capable of solving different problems using the same hardware. So the code changes. So it is more like each one of us gets a new notebook, but we all solve different sorts of problems, right? So maybe the 4th grade student will be solving their problems, and maybe a 10th grade or 12th grade will be solving different sets of problems, but the notebook what they use is the same. So theoretically speaking, they call this as a Turing machine, where you have all the symbols stored in an infinite space. So the infinite space is more of a notional thing, in the sense you are given enough space for you to write all the symbols and do most of your arithmetic and all the intermediate steps. That also you can store them back into it. So that's where we introduced variables, we introduced control structures. So if you look at it, it's more of a mechanical way of how you solve problems using simple notebooks. Okay, but the same thing has been actually manifested into computing. So what's hardware then? So hardware is nothing but the physics behind faster and reliable notebooks. But how do you construct those notebooks, right? I just want to differentiate here. The notebooks do not just mean only the laptops or the notebooks what we are currently carrying. So the notebook in the context of what we used to do during our school days, right? So it is more of the analogy is that. So the physics behind faster and reliable notebook, collectively I call it as a hardware. So this includes CPU, memory, I/O, storage, or any other devices or any other electromechanical or electronic devices that are behind hardware. Okay, so now that we write some program to solve this problem, so each program, or we call it as an algorithm, right? So how do you really measure the complexity of it? So it is more like, suppose you do a theorem proving on your math notebook, or you do some simple arithmetic. So definitely there is a complexity between both. Of course, though you believe that both of them sit in the same notebook, but definitely the complexity of doing one is certainly different from the complexity of doing the other. So in the modern computers, so what actually is going to determine the complexity of the code? So there are two dimensions to it. So one is the space it takes, like the amount of data it's going to consume, or the amount of instructions that you would require in order to solve a particular problem, and the time it needs to run. This is where people classify it, right? Where you have some programs they converge pretty faster in time. We call them as a polynomial type of algorithms, and there are certain types of problems where you classify them as hard problems. In other words, they are called as non-polynomial deterministic algorithms. So I mean, let's not get into the details of algorithms here, but all I would like to make a point here is these two are the major dimensions in deciding or in determining the complexity of the code that we write. You might be just wondering, why am I really going from the computing when the topic is network operating system? However, there are certainly some basics that were drawn from here, to design the modern systems. So the operating system is actually one such code. So I call it as an intermediary code, okay, that binds the software and hardware. So you have so much of stuff to do on that notebook, but how do you really go about that? Can you just use all the space available in that, or you want to use it in a very efficient way so that you can do a lot more problems in the same hardware? So how do you really want to go about it? So it's more like how you have an index or content, right, in your notebook that actually gives you some sort of guidance, like how do you really use this particular notebook so that you make the best out of it. So I call this as the rule book on how to use the notebook. It could actually sit in the notebook itself. That's why even your operating systems lie in the same hardware where you run your software. But what are the challenges? I mean, is it the rule book saying that you just start consuming the pages as you like, or how do you really go about it? That's where the challenges come in. So some of the notebooks we don't really want to share, and for our personal notebooks we don't share it. But in this case, so you will end up having more users using the same notebook, so that there's a lot of contention because it's the resource is limited, and you have a lot of users are trying to solve a lot of problems. And more users, more notebooks. Let's say you have a set of notebooks. In computers parlance, you have set of processors, and there are a lot more users and a lot more programs, right? How do you really share these resources so that you maximize or you optimize the throughput of the system? And more notebooks in different locations. This is very interesting. As I said, the hardware is going to be governed by some of the physics laws, right? So obviously you cannot perhaps pack the entire set of notebooks or the processors or all the computing resources in the same location. So they will have to be distributed geographically across different locations, right? So the challenges are going to be still harder, okay? And what sort of code these users are going to run on it? Is it going to be just a simple code, or is it going to be real-time code, or is it going to be a rogue code? When I say rogue code, it's more like somebody just scratches in your notebook and just they don't care about it, right? So you need somebody to control that. So otherwise, this code can just bloat the entire notebook, and finally, you may not find it more useful. And real-time is a very interesting thing because it's more like whenever I need the notebook, it should be available to me, at that instant of time. So it's not that I can wait for a while because the problem I'm going to deal is so important and so urgent that I would like to immediately get use of these resources at the same instant of time. So it's real time. So these are all some of these parameters, that actually raise more complexities in designing such operating system. Let's just look at a few of those principles, on which we actually structure the entire operating system. If you look at it, this rule book, some of the principles I've outlined. Actually, it is not limited to this. It is just to enable you to think in this line. I'm just showing a few of these principles. So first of all, the rule book should have the knowledge of know-how, right? It should know what comes under this notebook, like what are the hardware that are available to me so that I need to control it, or I need to manage it, or I need to share it with the users, right? So that's where they designed the kernel, device drivers, interrupts. If you look at it, there are just a few of them. Of course, the operating system books will write pages about it. So basically it is more of the device drivers listen to the device, or listen to the hardware in a very closer proximity, and they get to know the status of the notebook. In the physics aspect of it is actually obtained through these device drivers. They interact very close with the devices, and they carry instructions, and also they obtain some of the status and keep them ready for the kernel to understand what can we do with the device at that point of time. Okay, so the kernel, as you all know, so that's going to be the I would say the heart of the entire operating system. So that's going to manage each device in certain principles. Like let's say if you take Unix, the kernel is structured in certain ways. If you take Windows, it is structured in certain other ways. Okay, so each operating system is designed to solve some specific problems, or it is primarily to provide some sort of platform, so that these hardware or these resources are efficiently utilized or used by the users. Okay, and of course efficient resource sharing. So this is where the scheduler comes in. So what are the policies that I should use before I give my resource to a particular user or to a particular program. It's more like, do you remember we used to have a single big large notebook where we partitioned them, saying that this I will use it for math, and maybe another division that I'll use it for science or English or for language. So that's exactly what we are planning to do here. Whatever that we have been doing with the notebook, that's what we are doing in the computer as well. That the one difference is in notebook we have some finite number of sheets and we have single user at most of the times. However, at the computers, so we have more number of users, and even the memory is going to be quite large, and that makes the problem a little harder for us. And for archiving purpose, so where we have the file systems as well as storage, it's primarily to ensure that my data, whatever that I write on the system, they're persistent. I mean, it's not that I write something, if somebody comes and overwrites it, it disappears. So rather I need a mechanism by which I'm able to archive all the data that I'm interested in, or even the instructions. So where we store the software as well as the data related to that. And do more with less, that's one principle. Always the operating systems go with that, where the concept of virtual memory came in, wherein it appears to you that, okay, so there's a lot of space available to you. However, using some of the techniques such as paging, where the operating systems ensure that a particular user or a particular process initiated by the user has a lot of space, a lot of runtime space available to it. Okay, but eventually they do a lot of swapping between your hard disk or between your storage and the main memory, which we call it as the RAM. Right? So by doing that, this is just one aspect of it. Actually, there are a lot more such aspects related to that, but that is driven by the rule that you do more with less resources. And of course, then you have something called collaborate, because it's more like, if you remember, go back to the mathematics notebook, we would have arrived at some results through some of the earlier problems or theorems, right? So that always we carried forward to some of the other problems, referring that, okay, using the equation 1.1 or using something that I'm going to use it here, right? So it's more like there are multiple processes that could actually work together in order to solve a particular problem. So, but the operating system should ensure that these sort of mechanisms are made available to us. So it's more like the notebooks. There are different notebooks. Each notebook might be computing something or might have some data in it. So you need to have a mechanism by which you are able to bring in those data together and try to solve it faster. So that's where you have the IPC, inter-process communication or inter-processor communication based on the context. Suppose if you communicate between the processor, you call it as inter-processor communication. If it is limited to only processes, then you have inter-process communication. Okay, and then sockets. Of course, this is where slightly the network dimension coming into it. Okay, so where you have sockets serve as a connecting points to send data or to receive data between two different systems that are located across the networks. And of course, user-friendly, where the user might want to leverage some of the existing services with the operating system. So the concept of shell or command interpreter, libraries, utilities such as compilers, loaders, linkers, word processors. So there are several such utilities or libraries that are available, right? So if you look at it, this slide actually kind of summarizes how the notebooks, in our analogy we keep talking about the notebooks, right? So the mathematical notebooks, you can visualize that. So there are different dimensions to it, like more users using the same notebook or more users using more number of notebooks, but they are geographically located at different locations, or maybe they are co-located. So whatever may be the configurations, right? But how the operating system is going to make use of these resources to the best of use in order to meet up the requirements of all the users, right? So this is more of, if you look at it, an optimization software, I can say. It's an intermediary code, but the primary purpose here is it always tries to optimize the maximum usage or utility of hardware resources. So that's the whole purpose of it. I can take few questions now before we move on to the network related stuff.
Yeah, the questions are shared with you.
Yeah, I'm going through them. Okay, one question is, I would like to know whether a network operating system can never be compromised, attacks, viruses, malware. If yes, then how can we overcome these problems apart from securing the router with passwords? Maybe I'll take this up during the network operating system, I mean the second part, because now whatever I've covered is up to the conventional operating systems. That's for computing. If I don't have operating system, this is the second question. If I don't have operating system, how can I connect to the network for executing the operating system instructions? I'm not sure if I get this question right. Suppose if I assume, how do I connect to the network to execute the operating system instructions? I don't know how to really reword this question. In other words, without the operating system, it's going to be very hard for any application programmer, to use the networking resources. I mean, if I interpret it, if I don't have the operating system, how do I connect to the networks? Let's say if I take the first part as the real question. So obviously, if you look at it, as I said, it's user-friendly, right? So it abstracts a lot of, lot of hardware-specific details, which otherwise any application must know about it. Let's say the example what I was talking about, the socket implementation. So Unix implemented this in a nice way, wherein you treat a socket like a file. You open a socket, you read it or you write to it, and just you close it as normally you do with a file, right? So that's a nice abstraction they have provided. Otherwise, imagine a situation, how would you really connect to a network or connect to some other device that actually is connected using some, let's say, a serial interface. When I say a serial interface, it can be a simple serial link, RS-232 link, right? So it's going to be a lot more harder for us to really understand how those signaling works, and when do I initiate the transfer, or when do I stop the transfer? How do I know there are no errors in transmission, and if there are errors, how do I really fix it, or how do I handle the status? So there are so many things that you need to worry about it. But on the other hand, operating systems allow you to abstract that, right? So that you always take it for granted, and even the status what you obtain or what you get in response of calling a particular operating system services are pretty clear, and they provide very comprehensive status for you, so that the application will do something meaningful based on the status what they get. Okay. Another question is the kernel code same for all types of systems? Okay, certainly not, because each kernel is designed considering a particular notebook in mind, right? If you take a multiprocessor environment where you have several CPUs sitting and perhaps sharing the same memory, or perhaps having their own distributed memory architecture, so definitely the complexity is going to be quite different, and the way how it's going to distribute the workload between these processors and loading the data between all these memory modules is going to be quite different, and also the policies each kernel is going to adapt is going to be quite different. Okay, so keeping that in mind, the operating system designer must think about different options. So what's the real key here? What is that I'm planning to achieve, or on what platform I'm planning to run this operating system? So considering those design aspects, you must actually write your own code. However, some of the code can be leveraged. As I said, the device drivers, right? Say, let's say a particular system is going to interact with some sort of I/O devices, right? It can be a printer, or it can be some of the input devices, or it can be a modem. So let's say these devices are going to be the same for for these operating systems. These device drivers can be leveraged. So otherwise, you will have to write your own kernel. And how much memory is required to install a network operating system? Again, it depends. Okay, so commercially, you have even operating systems run into few GBs, and also if you look at the original network operating system, which I would say the NetBSD, there is a history behind it, right? The Berkeley software distribution, it was written by college students, right? The Berkeley University students wrote much of the software. So if you look at it, that's pretty lightweight, and of course now we have even microkernel. So there are certain operating systems that takes hardly few megabytes, but still they are capable of doing a lot of networking services. But at the same time, there are some commercial operating systems. The size runs from even 1G to 2G, or even sometimes higher than that. Okay, another question is, does the real-time kernel helpful for network operating system design? Of course, the answer is yes. Because in network, as we would see it in the subsequent slides, network operating system by default is real-time system, because the packet arrives into the system, you must take a decision there itself. It's more like when I have it, when I have a packet, I must immediately answer to it. Should I forward it or should I drop it? So we will see it slightly further down in the slides. Okay, but the answer is yes. Okay, as I was talking, there's another question. I was just talking about status of sockets. So if we obtain the status of sockets, will it solve the problem? No, it won't solve the problem, but at least it will make the job easy for you. At least you will know whether the socket exists or the other end failed, or at least you will get to know as quickly as possible. And also the semantic, when I say semantic, the meaning of the error will be a lot more easier for you to relate than if you go to the chip level. In fact, the various data bits will be reported to you. So it's going to be pretty hard for an application to really interpret it and make some decisions for it. Whereas operating system filters most of them or abstracts most of them and just gives you only that really matters to you. So I'm moving on to the network operating system now. Okay, so here we are taking one particular case. Okay, we are still in the same computing, but just that this is going to be a one dimension more. Okay, so we are actually going to talk about the infinite notebooks. Actually, this is pretty much the new concept of cloud itself. You know, where how would you really get as many notebooks as you would need? Okay, earlier days, whenever we are really looking out for any computing resources, either we'll have to order one, or we'll have to go to a lab and we'll have to do some sort of experiments with those processors. But now with the social media and most of the online businesses or e-commerce or whatever, even what we do today, like most of us really spend more time with such social media, right? If you look at it, you are really looking out for some sort of infinite sort of notebooks, right? So you want you don't want any limits on that. Like even if you look at Google offers unlimited space of memory for you. Even for each email account, that's huge amount of space given to you. Okay, but how do they really go about it? So what really makes it possible, right? So this is a typical case of you have a requirement of connecting more notebooks, but they're all in different locations, but you want them in a seamless way. When I say seamless, it's more like as you keep turning the page of your notebook, though you might be reaching the end of your notebook in this location, but as you turn it, you should be able to get onto another notebook which might be sitting a few miles away. How do you really make it possible? Okay, and how do you ensure that the entire resources are viewed as a single large notebook for you that has infinite pages? So that's where the networks come in. Okay, but if you look at in the conventional systems, so all the processors or the memory, they are all connected using the hardware bus, right? So they are hardwired and they have some sort of speed characteristics, like it takes a few microseconds or a few nanoseconds to transfer data back and forth. However, on networks, you can't actually operate it at that level. So you have to certainly do it in a different scale, right? So now you will understand how hard it is to write one such operating system wherein the network should behave as if the data or instructions are available immediately to you. So how do you really make it happen using networks, right? So that's what the rest of the presentation will cover. So it all started from Unix, where it had the concept of streams. Okay, those who are familiar with Unix would know it, where the underlying data, whatever they treat them, like it can be files or it can be on sockets. So they actually always treat them as a stream of data flowing in, right? So that's what, if you really look at the way how Unix structured its commands, you'll be able to actually pass these streams from one command to the other commands, where you use symbols like pipe, redirection. You can do all that stuff. The concept was inspired by the way how normally the streams work, right? In the real time, your water stream, how it actually flows. So they felt that data inherently have this sort of nature. Data which is being processed by one application or one program will tend to be processed by some other application. Then that application will actually process them and may perhaps transform the data or do something about the data and produce something else. So then it will be again fed into another system. So they felt that it actually behaves more like streams. So they came out with an abstraction called streams and sockets, as I explained a slide before. So they actually worked as an abstraction when it came to networks. So which is pretty similar to how files were handled in Unix. Okay. So that's where it all began, where they actually gave you a feeling that, hey, there is a possibility of connecting different devices, but you still treat them as if you are able to access those resources as well. But finally, if you look at it, what's really doing, like now I'm just bringing you into the current architecture of big centers, data centers, or large systems. Finally, all the pieces of hardware, you call any of them, say storage, a grid of servers, cables, switches, routers, firewalls, wireless, whatever it is, okay, After all, what do? They carry out instructions and move data. And finally, the whatever the Turing machine, which I originally mentioned, right, where you are expected to have a huge amount of memory available to you, and you have some infinite processing capability available to you. So that is made possible with the help of networks. But all of them finally do only one thing. They either carry out some instructions or they keep moving the data between various systems. In short, or in a new perspective, if you look at it, it is all about creating one such seamless large notebooks for each one of us, so that each one of us gets a feeling that I have infinite resources with me, because I have lots of need to store data, to retrieve data, to communicate with my friends or buddies or to whoever I want to know. So, and moreover, I want to always stay connected with my people as well as to all this information that are available, right? So finally, we are actually moving into a world where this is going to be made possible. So that's what makes the network operating system very interesting and very challenging. So now suppose if we really talk about the same code, right? So earlier we saw that the code inside a notebook is determined, the complexity of the code is determined by the space and time. However, in this infinite notebook, there is one aspect that we cannot ignore, is the network. That's the third dimension. So earlier when we write any application, we used to always measure the space it takes and the time it needs to run, right? But now if you really look at it, most of them are online driven, right? So people always ask you, okay, it takes so much of space, it takes so much of time, but what's the network bandwidth it's going to use, or what's going to be the delay in the network, how much you're going to account for the performance of your system. Okay, so how these networks are built, okay? So this is where the concept of protocols come in, where protocols actually provide the foundation on which the networks are built. So I'm not going to go into the details of all these protocols. I assume that you know about OSI 7 layers. Each layer has got a set of protocols through which the entire the networks are built. And network OS, what primarily it does. So while networks provide the foundation for networks, while protocols provide the foundation for networks, network operating system provides the foundation on which these protocols run. Okay, so that makes it slightly different. So this is where we need to understand how things are shifting a bit. Earlier the operating systems' primary concern were sharing the resources, and the focus was more on computing. Okay, whereas on the network, the focus is more on communication, right? So now we need to transition these operating systems or adapt these operating systems in order to support powerful communication features as well. So what are the challenges? Of course, quickly we can immediately relate to it, where there is a paradigm shift from computing to communication. Okay, so while operating systems were primarily meant for computing, now the focus is being shifted to communication as well. And another important aspect is the motion of packets. So there was one question about real time, right? Why it is real time? Because nothing is static in the networks. So network means movement. That's motion, right? So certainly when it involves motion, if you really relate to some of the fundamental physics, certainly it has a lot of dynamics, right? So it has some rate of flow, like how faster it's moving or how slower it is moving, or what should be the guaranteed speed we need to provide so that these packets are able to travel. So actually the motion actually makes it real time, as well as it's more lively. It's always lively. Okay, and even those packets, if you really characterize them in a broader way, you have data, you have voice and video. So all of them are actually moving inside the network. And of course, there are a few more other dimensions I've added here where you need to do some sort of multicast. and security. This is very, very important, okay? Because it's going to be more like streams moving out, right? So the packets are going to move between different devices because that's what we are actually accessing the information, okay? If that's the case, how secured are they? Because we might be carrying some of the sensitive data, since it's going to be stream and you're not going to own the entire network on which you are going to transmit the data. How do we really ensure that the security is taken care? So if you really look at it, the operating system that are primarily meant to share memory, to share some of the storages, to share some of the processing capabilities, here you really see a world of other dimensions or other parameters that are coming into it, you know. And of course the physical media. This is very, very interesting thing, because the physical media, if you really look at it, each one will be operating at with certain parameters, right? So one such example is the maximum transmission unit for each protocol. Let's say if it is an Ethernet, you will have some packet size. If it is going to be an optical link, you have some sort of MTU. So basically they are all going to be different. That makes it still harder for us. It's not going to be uniform. When I say the motion of packets, at least if they are going to be motion of similar packets, you'll have at least some ease of control on it. But here we are going to deal with the packets that are going to be different in sizes, but they're all going to be moving. So now we can actually understand how difficult it is going to design an operating system that's going to really support this. So what's the single most important design consideration of network operating system? So to me, if we really put it in one statement, it is this: a packet should spend the least possible time inside any device. Okay, it can be a router, it can be a switch, or it can be a gateway, it can be anything. So can we really ensure that a packet spends at the least possible time so that it can always travel at line speed? If any operating system which is going to help you achieve this, then you have a perfect network operating system. Okay, so the requirement or the design consideration is pretty easy to state, but I know at least in real-time implementation, it takes a lot of effort, it takes a lot of intelligent algorithms in order to achieve this. So there are a few more terms that are coming into this. Of course, when we talk about network, it talks about abstraction, right? Because the very concept of 7 layers is abstraction, where each layer is confined with what it wants to do, so that the above layer does not need to worry about the lower level details, right? So the abstraction. Of course, the OS must ensure that enough abstraction is possible by any of these protocols. And of course, topology, because network topology is it's more of how many different ways I can connect these devices. You know, like should I have it in a kind of a daisy chain, or should I connect it like a star, or should I connect it in a random fashion, or should I connect it in certain other ways? So it's basically the way how these nodes are connected. Of course, packets and frames, I don't want to get into the details. So they're all sort of abstractions. You know, instead of talking about bits and bytes, normally you talk about packets and frames based on the layers on which the data are going to be operated. And important thing, you have something called control path and data path, right? Control path is basically, you know, the signaling. You know, like you establish the connection and you ensure that enough bandwidth is guaranteed or is made available, and the status are properly set so that you're all set to communicate. Okay, whereas data path is the traffic itself, the payload, right? Of course, then you call something called traffic flows. The flows is a very important abstraction, right? So the flow is basically, you know, the set of or sequence of packets. They are all destined to the same destination or for the same application. You call that as a flow, right? Because it's very important that you maintain the order of the flow. So otherwise, there's going to be a lot more overhead at the end, at the receiving end, to reorder these packets to ensure that the flow is rightly maintained. Okay, so we will not go into the details because the focus will shift into the protocols then. But our focus will be more on the networks, I mean on the operating systems. How operating systems will understand this and will try to provide support to all this. Of course, sessions. So they are all some of the trivial things, but just the idea of this slide is to bring you some of the different concepts that come into the network operating systems that are not there in the conventional operating systems. So there are three functional blocks of any networking device. So you have control plane, you have data plane, and you have management plane. So the control plane, as you see it, it's all about packets forwarding. Sorry, I think I skipped. Okay, so this talks about the data plane. So data plane is all about forwarding the packets. So this is very responsible for deciding what you want to do with the packet. You know, like the moment the packet comes in, you want to put it onto a particular path. You know, so if you look at any networking device, you'll have different interfaces connecting to them, right? Something will be in bringing the data in, something will be bringing the data out. Okay, and then this is where the packet scheduling happens. You know, like which packet gets what priority, because there will be a lot of flows maintained in the same device. So how would you actually do the scheduling of those packet flows? And of course, queuing comes in here. Let's say you are not able to really forward it as fast as you can. So obviously, you'll end up queuing these packets. Control plane. This is where this is the responsible. This is responsible for signaling, routing, and constructing the forwarding table. Signaling, as I explained before, it's more of setting up the sessions or exchanging some control information. You know, this is where the status will be exchanged between participating protocols, and ensure that it is all set for communication. Then routing. So routing is very important. It is basically to decide which path to choose. Any network device, the moment it gets a packet, it should decide how do I send it next. Okay, so constructing the routing table itself is a very important area. It's a key challenge in designing a network operating system. How efficient are we going to construct the routing table? And third aspect is how do we construct the forwarding table? Okay, the slight difference here is in routing you decide the path, which path you want to take in order to reach the destination. So the forwarding table is more like what would be the next hop you want to take, because once you identify for a particular flow, this is my next hop, for the subsequent packets in the same flow, you don't need to actually keep doing the table lookup in the routing. So rather you can always look up the forwarding table and all the packets destined to the particular destination can be immediately put up into the next hop using this forwarding table. Management plane, this is where you deal with the network management. Since they are all going to be distributed at different locations, you need a very stronger management framework, at least to get to know the status, or to control the devices, or even to provision the devices. Let's say you want to ensure that there are enough bandwidth for a particular video session or for an audio session, or you want to ensure that you want to restrict some of these users, so where you don't provide access to all the users into the network, or you want to ensure that there is enough QoS guaranteed. So in the management plane, you enforce certain policies, and there are certain parameters you set in so that you expect the network to behave in certain ways. So like how we did in the math notebook, where you have multiple users using the same notebook and different combinations. Similarly, here you have all those three planes could share the same processing units, or they could run on different processing units. Okay, so basically, if you want to provide a high capacity device, a router or a switch, then obviously you will end up having different processing units for different planes, because that makes it very faster. For example, the control plane would keep computing the routing tables and update the data plane, saying that, hey, this is how the topology keeps changing, and this is the modified or the up-to-date routing table, so that the data plane does not need to worry about how do I really compute these routing tables. Rather, they could just use these tables and straight away forward the packets that are arriving in. Okay. This is basically, for different, let's say if you are going to have different processing units. So certainly then you need to have some sort of powerful coordination mechanism between these processing units, because control plane, data plane, and management plane, all these three should work together. So certainly you need to employ inter-processor communication, which is basically, how all these three planes are going to communicate with each other. Message passing, this is between these units, like how they are going to synchronize, how they are going to exchange information between them. So for exchanging information between these processing units, you have various infrastructure supporting that. So one of them is message passing, and of course you need to have certain synchronization principles. Let's say the routing table itself, right? So there's a lot of changes happening in the network, and let's assume that the routing tables are going to undergo a lot of changes. How the data plane will quickly get to know this is the current table that I need to use. Okay, one such scenario. So number two would be, let's say you detected a security vulnerability. Let's say somebody else had broken into the network. You quickly wanted that session to be terminated. So suppose you got to know it at the control plane. So how do you ensure that this is communicated to both? So let's say you got to know it in management plane. How do you immediately communicate to the control plane as well as to the data plane, right? So you need to have very powerful synchronization mechanisms between them, so that all of them work together in unison to ensure that there is no issues of integrity, in the way how they function it. So some of the primitives what the OS should provide are queues, buffers, schedulers. As we have seen, queues are primarily meant to temporarily hold the incoming packets, and not just to temporarily hold them, even they would actually decide how do we really prioritize this incoming traffic, how do we prioritize the flows, how do you do analysis such as the deep packet inspection, how do you really ensure that it's a very rogue traffic that is coming into it. Somebody is just pumping a lot of traffic into your server to really, deny the service that is offered by your server. So how do you really go about that? And of course, buffers, which is all about memory management. I mean, here the buffer management is slightly different from the operating system's buffer management. Okay, because in the operating system, at least each process will request for a particular amount of memory, and right up front, the process will be given or granted or will be denied based on the availability. However, in the network, it's quite difficult to predict the length of the flow. In other words, like at what rate these flows are going to come and how long it's going to come in that way. So in such cases, how do I really ensure that enough buffers are really reserved for a particular flow? So they are all very interesting optimization problems, and how best the operating system is going to support that. And of course, schedulers. This is quite similar to the process scheduler, but here the whole concept is going to be based on how do you really match the incoming rate as well as the outgoing rate of packets, and how do you ensure that the schedulers are smarter enough to ensure that these packets are rightly placed in the right queues and they are forwarded further. So some of the algorithms or some of the primitives what the operating system is expected to provide. Let's say if it is going to be a router, so certainly there should be powerful routines or powerful structures should be made available for table lookups, because it's all about the destination route lookup, right? So the moment the packet comes in, you got to figure out to what destination it goes. Do I have a route for it? So I got to search for it. With the internet growing at exponential rate, so certainly these routing tables are really growing larger. Okay, so how faster you can look at the table? I mean, should you use hashing techniques, or should you use any tries or some special data structures? So how efficiently you are going to organize them, or how distributed they are going to be? Because this routing table is going to put a lot of challenges, both in terms of space as well as in terms of lookup table, right? Because they're going to be large, and with the IPv6 coming in, you have lots of address space, so certainly the destinations are going to be quite larger, and it's still, I would say, one of the hard research areas to even design the routing tables for IPv6. And of course, for switching, let's say if it is going to be a switch, it's going to immediately find the next hop and how sooner it's going to index the incoming packet, right? Let's say there are about 4, say ultimately whatever the amount of destinations you look at in a particular networking device, you will eventually have fewer outgoing interfaces, right? So among them only you're going to choose one of them, right? So that's where the indexing coming in. And nowadays the routers or the networks are going to offer lots of services, based on the user subscription, based on different types of applications that are running on the network. So certainly the packet classification is very important, and of course the pattern matching is one such technique that should be supported in the system, so that you are able to make use of that in order to do a lot of packet classification. And another key principle that we need to figure out is zero copy of packets. Let's say the packet comes in, so certainly it will be maintained in one buffer, right? Because you've got to take a decision. What do you do? What do you want to do with the packet? But if you really look at it, we all know that in a TCP/IP model, it's going to be 4 layers. But if it is going to be on a OSS stack, it's going to be 7 layers, right? How do you ensure that each layer gets access to this packet, but without you making a copy of it? If you really look at it inside the router or inside any network device, copying the packet is going to be the most expensive thing, because just now we have seen the packet is going to arrive at the line speed. Let's say if I'm connecting to a 100 Mbps link, then it's going to arrive at that particular rate. If it is going to be 1 Gbps, it's going to arrive at that particular rate. So the packets are going to flow, and particularly if you take video or some of the real-time traffic, it's just going to flow in certain rates. But at the same time, inside the design of the operating system, how do I ensure that these packets are rightly maintained, placed in certain buffers, so that the rest of the layers, instead of making a copy of these packets, they are still able to look at the packets. I can just quote one example where you can appreciate this concept and also the challenge involved in designing such a mechanism. Let's say the incoming packet arrives on an Ethernet. The outgoing the outgoing interface is going to be, let's say, token ring. Okay, just to illustrate it with 2 simple examples. The maximum transmission unit for each protocol is going to be different, right? So the frames, the moment they arrive in, for Ethernet, it will be, say, I think 1040 or, so it's going to be of that size. If it is token ring, it's going to be of a different size, right? So certainly at one case, you may have to fragment them and send it. At another case, you may have to assemble them together and send it. Let's say if the MTU of an incoming interface is going to be smaller, then you are going to assemble them. If you are going to assemble them into single large frame and send it out. If not, it is going to be, let's say you get a larger frame and your outgoing interface is going to be a smaller frames, you will have to fragment them. But all you need to do it inside the memory, right? How do you really make it as a zero copy? This is a very, very challenging thing, and in fact there are a lot more ways to do this, okay? But how efficiently the operating system is going to provide that support to you, so that the moment the packet comes in, without actually moving that data from one memory location to another memory location, can you actually achieve this? Okay, this I would say, to me, is one of the most single design consideration. Can we really write an operating system, network operating system, that just guarantees a zero copy of packets? And then you need to provide support for protocols, right? So the way how protocols function, they are all perfect state machines. If you look at any protocol, the protocol will always have a start state, and based on some of the events that are happening, it will keep moving on to different states, and it will always remain at a particular state where it can wait for the next event to occur. Okay, and then it will have the final state, it will have some error state. So it's basically a perfectly, a prefixed, a predefined state machine. So that's why in networks, the peer-to-peer communication is going to happen without any difficulties, because both the participating parties will exactly know in which state they are in and in which state or which event they are expecting next so that they can advance their states, right? So how best the operating system is going to provide support for such state machines so that the protocol developers, they don't need to really worry too much about writing their own state machines. Rather, they define the state machine and leave it to the system so that the system actually, implements the protocols with a lot more ease. And to answer this, there was one question in the previous session. It was about the real-time events, right? So definitely you need timers and interrupt handlers to take care of that. Okay. So in fact, most of the operating systems will have very powerful timer structures, because how long the packet can reside in the queue. I mean, at what time you will decide that you can discard the packet. At what time you will actually raise an alert to the higher layer. At what time you will say that there is an overflow situation or an underflow situation. So there are several events, and how do you really decide that? So certainly the timer connected with the protocols is going to be very powerful. So while actually timer is still important in the conventional operating system, but in networks, I would say the network operating systems cannot live without the timers, okay? Because each event is eventually driven by various timers that are set, for the protocols or the packets or for interfaces. If you look at it, they are all driven by timers, okay? So even in timers, you'll have different types of timers. One is, you can have a passive timers wherein you poll the code what you write will keep checking whether the timer is expired or not. You set the timer and you keep it expired, check for it. There are certain active timers where they will interrupt you saying that, hey, this is up, your time is up, now you have to take some decision, okay? So in fact, each packet, the moment they get in, they'll be assigned a timestamp saying that, hey, this is the time you got in, so that they are able to take a decision at what point of time I can actually, say that, okay, this is too long a time that this guy is living inside my system, so it's time that I dump him, right? So they're very important. And the interrupt handlers, they're very powerful because since it's real time, so the real time events always happen through interrupts, either a hardware interrupt or a software interrupt, right? So the moment the interrupts happen, whatever the job you have been doing, maybe you are constructing a routing table, or maybe you are checking a security aspect of one particular connection, whatever that you might be doing. So based on the priority, you should be able to go back to the interrupts and handle them, right? So these are some of the primitives that are related to that. So having come so far, if you really look at it, the real trade-off, the real challenge here is this. At one end, we are talking about the network layers abstraction, right? Because you have multiple layers, each layer will be worried about its own job. Whereas on the other hand, you are actually expecting a line speed performance, right? Because each layer, even the zero copy is one such example, right? So let's say the physical layer gets this frame, but to the data link layer, should they copy it or should they share the data? How do they really share this information? Let's say the data link layer has to put it onto the network layer. But network layer, so certainly the layer approach works very well for accommodating different types of devices, different types of physical layers. It's basically to support a diversified system of network. That's agreed. However, the performance-wise, we are always expecting to achieve the line speed. This is a perfect kind of, I would say, a paradoxical requirement of network operating system design, right? Because let's say in the physical layer you have the data, and let's say the network layer is going to take some decision on this packet. So how this information is going to be passed? Are they going to be in the same shared memory? If they are going to be in the same shared memory, how well they are going to be, still maintaining the layer abstraction, or will the network layer get to know what's really happening on the physical layer? Should we really make it happen or should we not? So at one end, we want the layers to abstract them. At the other end, we want each layer should operate on the same data without actually making a copy of it. So this is one example of a perfect trade-off, right? So that actually opens up a lot of challenges as well as different ways in order to achieve this trade-off. Okay, so if I really summarize it, writing a network operating system or designing a network operating system fundamentally lies on this trade-off. So coming back to this, what's the one key principle that we need to follow? I would say those principles are some of the design considerations. However, at least in my experience, I've seen that there is no one single principle that fits all possible situations, because each network device has its own purpose and what it really wants to do. However, the design consideration, as I was explaining in the earlier slides, that it must actually do the entire thing at the line speed. In the sense, is it possible to devise a network operating system that supports the protocols and the networks in such a way that we don't drop any packet? In other words, there is no retransmission. If we keep that as a single goal and design an operating system, so definitely that's the motivation behind the whole thing. But however, it's not just one simple way to achieve that. It really requires it's a lot more intelligent algorithms, a lot more ways of designing data structures, and even a lot more support from the hardware. Like let's say if it is going to have multiprocessor environment, so how we are going to designate different processor for different planes, even that decision will make a lot more impact on your system. So this is where, if you really look at it, either commercial operating systems or whatever the open source operating systems, if you look at it, so they are all differentiating themselves at certain dimensions, but fundamentally their goal is the same. So can we really achieve the line speed, so that the dream of each one having an infinite notebook is made possible. Okay, so with this I conclude this session, and perhaps I will go over some of the questions that are posted here and try to answer it. Okay, I'll go from the last question first. Which data structure is best for routing table? A lookup, that is basically a trie, which I was mentioning. I think the answer is again, based on what we do about it. Let's say if it is going to be a simple IPv4, certainly tries are very good, lookup structures, where you can certainly achieve it in a predefined, prefixed constant time. However, let's say if you go with packet classification, where you don't classify only based on one IP address, right? So you will actually classify based on source address, destination address, or a particular port. So basically there are different parameters in the network packet you will be using in order to do a lookup. In such cases, even some powerful hash tables will be helpful, or a combination of tries and hash tables can also work. Okay, are there any standardization in designing the network operating system for all vendors? Okay, most of the commercial operating systems are proprietary, where their implementation details are not disclosed, because that's what they believe is going to be the differentiator for them in the market. I think this will continue for some more time before any open source operating systems really take over. Of course, there are very nice operating systems, particularly the NetBSD, which I was mentioning about. So they offer good services to design. I know they offer, there's a well-developed tested code that people normally leverage to develop their own network operating system, of course by customizing or by standardizing something. Some of the standardization techniques, what I can do is I can code this the way how the protocol is going to be structured. For example, the finite state machines. So most of them actually use the finite state techniques. Okay, so from the design principles, I would say there are a lot more standardization. But if you ask for a specific standardization, or is there any accepted standardization for network OS, the answer is no. Okay, if routing loops occur, how to clear it? That's another question. That's a job of the routing protocols. So all the routing protocols have these conditions in mind while they discover the new paths. So that's, I mean, the network operating system does not need to worry about it. So the routing protocols will worry about it. Okay, this is a very interesting question. How do we relate the concept of cloud computing with network OS? Actually, going back to the principle, this is exactly what I was trying to address, right? So the cloud computing is made possible only with a network, right? So it's wherein earlier we were talking about for computing, then we were talking about for communication. So cloud is, I would say, an unification of both, where you compute as well as you communicate, right? So certainly most of these principles are related to the cloud computing. In fact, cloud computing is the realization of having a powerful communication infrastructure and having a computing infrastructure on top of it. And most importantly, everyone gets a feel that they are given an infinite access to computing. So most of these concepts are certainly related to the cloud computing OS also. Okay, what's the minimum bandwidth required so that the network operating system runs properly? Actually, bandwidth is not related to this because bandwidth is related to the traffic. This is more of the system configuration. So for a network operating system, what you need to worry about is how you really structure those interfaces. Let's say the packet arrives in a particular interface. From that interface, how you are actually taking on to one of those three planes. So how that hardware is going to be structured. Is it going to be totally hardware controlled, or is it going to be a combination of hardware and software, or is it going to be software driven? Or even if it is going to be a hardware, what sort of architecture we use inside, the system architecture. That's going to determine the performance of the network operating system. I'm picking most of the relevant questions, and some of the questions that are not in the context, I'm not taking. What are some high performance network operating system? Okay, so certainly Cisco IOS, Junos, even NetBSD, to name a few of them. Okay, are we trying to tie all the OS on every device? I mean, do we have any unified OS? Okay, so that's the whole objective here. In fact, since most of the devices eventually end up taking care of the packets, right? What you do with the packets? That's a fundamental question put forth for any operating system, any network operating system. So you may not have a unified operating system, but some of them you can leverage. For example, what the operating system that is running on a switch and that is running on a router, you can have most of them sharing the same infrastructure, except few for routing. For example, the table lookup, how the routing protocol is going to converge, and what sort of timers you will have, and what sort of data structures you are going to support. That's where the difference will be. Okay, but fundamentally, most of the principles will remain the same. Okay, is policies of firewall depend on OS structure? It does not depend on OS. It depends on how the network administrator configures the firewall. However, one relationship with the OS is how far the OS is going to give protection to the data, right? So let's say there is a packet that comes in. So on the physical media, let's say we can provide some kind of encrypted data so that people don't intercept and try to read the data. However, once they are into the system, can somebody inside the operating system with the root access, can they actually disturb the traffic, or can they actually tamper it and try to take a copy of them? How protective the operating system is. So that's where the operating system comes in. But as far as the policy is concerned, I don't think network operating system has any role in it. Okay, how does abstraction help the flow of data to be limited to its application and not stray into another application? So this is what typically the flow concept comes in, right? So each packet will be handed over only to the port it is destined to. It is not only to the device, it is also inside the device will have multiple ports. Ports are kind of, I would say, logical entities. They are not physical entities. So let's say in the same computer you can have, say, hundreds of ports opened and made available. So the network protocols will ensure that it maintains a context of each flow. They don't really mix up the flows. Okay, so these flows are maintained in its own context, and they're handed over only to that application. So there is no question of these flows getting mixed up and given to some wrong flow or some wrong application. That's not possible. So I think I've answered. Okay, there is one more question. How is the packet scheduling done in DDoS? Okay, I don't know about DDoS. So, but generally, if you ask me about how packet scheduling is done, there are different scheduling algorithms available. Like for example, first in, first out, and also some sort of round robin method available, and priority queues are available, and even some of the standard packet schedulers, that are based on some powerful queuing theory techniques. They're available. Okay, and also it is based on the QoS that we are setting. So the scheduler's job is to understand the QoS requirement of each flow and then take a decision for each arriving packet. So that is how it is done. So I guess that's all for the questions. So with this, if there are not any questions, I will conclude my session.
There are a few more questions.
Thank you very much. Yeah?
There are a few more questions shared with you. Can you see them in the questions pan?
Oh, okay. No, I'm saying that I answered all of them. I answered most of them. Okay, there is one more question, sorry. So, which primitive network operating system is the best to study for students or beginners? At least I learned it from NetBSD. So the answer is you learn it from NetBSD, which is also free. Okay, what is the best network operating system in terms of throughput and why? Okay, I haven't done any comparative study yet. Of course, there are some market research that says under certain conditions iOS is better, that is Cisco's iOS, and certain conditions Juno's. But I don't have any supporting documents to really conclude that this is the best or that is the best. Okay, so each one has their own benchmarking, and they are meeting some of the criteria. I mean the speed criteria. Okay, will cloud cause a stress to network OS as a lot of intricacies involved in network streaming? Yes, this is very much true. It's not just a stress. The network operating system even must evolve. That's what even in the title I mentioned, that it's for evolving networks, right? So the whole challenge is that, see, it is still not matured yet, because in cloud we are also moving the computing capability. It is not just the data being moved between the systems. It is also the computing element. Let's say even the code, what you're expecting that to execute, even that can actually move around, that can be distributed. Actually, cloud is changing the entire dimension of computing and bringing network as the key parameter that helps you achieve that, right? So that's going to be a lot more intricacies, and certainly we must evolve a lot of primitives. As I said, the stream is one such primitive, right? Perhaps for a cloud in a distributed environment, how do you structure these streams? How do we ensure that these streams are optimally routed, or how do we ensure that these streams are efficiently transmitted between the systems? Even the best question is how the cloud should be connected. Even the topology is not fully solved yet. So the way how I look at it is just I would say a beginning of some grand things, but still a lot more to do. So there's a lot more scope and challenges in designing such operating system. And I'm skipping the protocol related questions because that requires a different forum. Okay, can a network operating system ever be compromised? Yes, it can be compromised. there are several instances we can quote, right? So the worms and even denial of service attack and hackers who actually always get into your system, access your login and try to inject some malformed packets, or even simple, they can just bombard your device with so much of traffic that your system cannot handle. They all will appear very legitimate for your network device. You know, they will think they are all very normal traffic, but it's going to be pretty hard to really figure out, is it going to be a attack on your system or it's a very legitimate traffic. So of course network operating systems are very vulnerable, and in fact any operating systems are primarily tested for its security vulnerabilities first before they are deployed into any devices or any service providers. Okay, so that's it. So
I think
I
we can
answered
conclude
most of
now.
these questions. Okay, so thank you so much. Thanks for listening to me for the last 1 hour 20 minutes, and it's really my honor and pleasure to share what I learned in working with a network operating system. So thanks for the opportunity given to me, and thank you so much.
Thanks, Mr. Vaniyarajan, for your informative session on network operating systems for evolving network. It was indeed an enlightening session. I would also like to thank our participants for their support in making this webinar a huge success. The recording of this webinar will be available on techgeek.com by tomorrow. The next session in TechGig webinar series is happening today at 5 p.m. Topic for the webinar is Adopting Scrum, a case study involving transition, implementation, challenges and benefits. We will be having Mr. Deepak Vijayaraghavan, Senior Manager Delivery at Nest Technologies as our guest speaker. So see you all at 5 p.m. Thank you.